So with applied optimization, we're going to look at various word problems. And what's going to come through and how this relates to optimization is the idea of maximizing and minimizing functions in context of a word problem. And where those are going to come through is, as we talked about with graphs, that's where we had local minima and maxima. So what we're going to do is look for critical points with the functions that we form. So when we want to minimize and maximize, we're going to develop a function, and then we're going to solve for where does the derivative of that function equal 0. So our first examples here are going to deal with geometry. So we have a rectangular garden is to be constructed using a rock wall as one side of the garden and wire fencing for the other 3 sides. So we're going to have a rock wall and then 3 sides of a wire fence. Something like that. That's our wall. And we are given 100 feet of wiring, and we want to determine the dimensions that would create a garden of maximum area. So we want to maximize area. So what that tells me is that I want to find a function for area, and then I want to find critical values of that function, of where does the derivative of that function equal 0. So let's start putting it together. So we are working with wire fencing, and we have these 2 side lengths. We have x, and then some length y. And what we know is the length of all of those together is 100 feet. So 100 is equal to x plus y plus x, or 2x plus y. So we have this relationship coming from the perimeter of those 3 sides. What we want to do is talk about area, which is going to come from x times y. Now, working with that function of area, if we just use x times y, we're in a little bit of a bind there because we have so many variables. So instead, what we're going to do is from that first equation that dealt with perimeter, I'm going to solve for y. So I could put everything in terms of a single function. If I want to call this a of x, I'll have x times instead of y. It would be using 100 minus 2x based on the relationship from the perimeter. So we'll have 100 minus 2x. And we could go ahead and simplify that out. So we have an area function that's going to come from 100x minus 2x squared. So that is for area of this 3-sided wall that has a length of walling that is 100 feet. So now what we want to do is maximize this area. So we're going to take the derivative, which is 100 minus 4x, and we want to solve for where is that equal to 0, because that should be finding our critical points that would be making a maximum or minimum, and based on the construction of this, it's going to automatically find a maximum for us. And we can kind of see that at the beginning where we just had a of x. This is a parabola that opens downward. So what we're doing is we're finding the vertex of that parabola, and we're using derivatives in order to do that. So add 4x to both sides, divide by 4, and we have a side length of 25. And now what I want to do is go back and find out what was the question. Determine the dimensions that would create a garden of maximum area. So we're going to have a side length of 25, and the other side length is going to come from 100 minus 2 times 25, which is 50. So the dimensions are going to be 25 feet by 50 feet for a maximum area of 25 times 50. And that will be 1,250, and then our units would be square feet. Okay, so putting things together to have a function in terms of a single variable, find the critical point, and that's going to help us form our solution that maximizes area. And then what you could do is double check your answer as long as the function's set up correctly. So when we got to the point of just having a function for area with the 100x minus 2x squared, and the idea was that we were finding the vertex of this. So if we throw this into a calculator and go searching for that vertex way up here, it's got to be there somewhere. There we go. There is our input of 25, and then again this is calculating area, so there's our area of 1250. Okay, next one. We have an open top box is to be made from a 24-inch by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. So what this looks like is we're going to have a big rectangle of cardboard. Like that. One side is 24 inches and one side is 36. And what we're doing is we are cutting a square out of each corner. And that allows us to fold up the sides and construct an open top box. Ooh, let's try that one again. Something like that. Okay. And we don't know how big this square is going to be, so we're going to call that x by x. So when we cut those out, we can then fold up those sides and like tape them together, whatever we're going to do, in order to make our box. What size square should be cut out of each corner to get a box with maximum volume? So we want to maximize volume of what will be an open top box. So we're going to have something like this at the end where it's open on top after we fold up those sides. And we want to maximize that volume, which usually comes from width times length times height, but that has way too many variables. So we're going to try to simplify that just in terms of a single variable, relying on x for the side length of those squares. So what we need is this length right here is an actual side of our box. So we don't want to use 36. Instead, we want to think of 36, but with two of these squares cut out. So really that length is going to come from 36, but then take away two of those x values, since we're taking away two squares. Similarly, one of the other sides, the width of our box, is coming from that 24, but it's 24 with two of those squares removed. So really it's going to be 24 minus 2x. And then the height of the box is coming from the square side length, and that's going to be our value of x. So for volume, in terms of a variable of x, we're going to have width, which is 24 minus 2x, times length, which is 36 minus 2x, times height, which is x. And then we could go ahead and simplify this down. I'll go ahead and distribute x into this one right here. So we'll have 24 minus 2x, 36x minus 2x squared. And then I'm gonna FOIL. So let's see, 24 times 36 will have 864. Nope. 1 second. 24 times 36, yeah, 864. X minus 48x squared minus 72x plus 4x cubed. Okay, so our volume is coming from 4x cubed minus 48x squared And then let's see, 864 minus 72 for a 792x. And I found my error. I felt like I went too fast there. That should be a 72x squared. So what we'll have here is instead negative 48 minus 72 for negative 120x squared plus 864x. Okay, there's our formula for volume, and we want to maximize this, so we're going to go looking for our critical points. So let's take the derivative for a 12x squared minus 240x plus 864, and we want to see where this is equal to 0. And I'm going to go ahead and divide out a 12. 12 goes in nicely into everything just to simplify it a bit. So x squared minus 20x plus 864 divided by 12 is a 72. Just for some simpler numbers to work with. I could try to factor this, but this actually isn't going to be factorable. So to solve for x here, we're going to use the quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. And since we're just getting decimals out here, we can just go ahead into a calculator to get our two answers out. And let's do that together, because why not? It's been a while with the quadratic formula. So we're going to have 20. Let's do plus first. Square root of 20 squared minus 4 times 72 all over 2. So we have a 15.29 as one of the answers. And then we do the same thing, but instead of addition, we're going to use subtraction. So 4.71. Now, two solutions are coming out here, and I want to see what makes sense. So to have a 15.29 is going to be impossible because one of the side lengths is 24 minus 2 times our value for x. And if I do 24 minus 2 times a 15.29, it's going to end up negative, and I can't have a negative side length. So it's not that we have two solutions, we really have one. We just have to throw it back into context of what's possible, and that 15.29 is not possible. So we have one solution, and it's the 4.71. So what size square should be cut out of each corner to get a box with maximum value? The side length of the square should be 4.71, and my units are going to be in inches. And they didn't ask for what the volume is, so we can leave it just like that. Okay, we have some more examples on the next page, but I'm going to go ahead and end this video here, and then you can watch the next one for the rest of the examples.